It's lovely to see so many of you. And my name is Christian Holm. I come from the Center for Medieval Literature, as does Christian Etheridge, who will be talking on exposing the flat earth and other myths. We at the Christian is a PhD student at the Center for Medieval Literature, which is situated just across here somewhere, down another corridor. You'll find us. I think Christian is a very good example of what we are doing at the Center for Medieval Literature. Literature is meant in the sense of any kind of writing that we treat across disciplines, across languages, across all the things that normally divide or subdivide the medieval world into nations, languages, fields. So science can talk to literature, can talk to religious text, and so on. And Christian in himself has also done that kind of sort of working across disciplines, I would say, having done much work prior to this on trade, so trade routes in the north, in the medieval age, and it turns out that many of these exact same trade routes are the routes by which knowledge of science was distributed and channeled through, people carried one sort of thing and other sorts of things, either physically or mentally. But today it's more into the world of myths, perhaps, of science. So please, Christian.
Thank you very much, Christian, for introducing me, and thank you very much for the organisers for inviting me here. And it's very interesting for me to address a crowd which isn't just medievalists, but is also scientists as well. So I hope to kind of like introduce you in this paper to the idea of medieval science. Now, the whole thing with the flat earth and why I call it the myths of medieval science is because there's been a great popularity that science in the Middle Ages wasn't science, or it did not exist. There are great discoveries in the classical area, especially with the Greeks, and then there was a kind of like a downhill slope where nothing much really happened, especially due to the Catholic Church. And then the Reformation, the Renaissance happened, and then science sprung up again and continued its glorious journey to where we are today. However, this is not actually the case, and this is what I'm going to explain as I go through today's paper. Now, I begin with the flat earth. And here we have a modern representation of what such a thing would look like. So, did people in the Middle Ages believe this? Well, we have one example, and this is Cosmas Indicopleustes, and he was a 6th century Byzantine monk. He wrote the book, The Christian Topography. Now, he aimed to prove that the earth was modelled on the tabernacle. And the tabernacle was house of worship, appears in the Bible, and so therefore was flat, and the earth was flat as it must follow the Bible. Now, the great historian of medieval science, David Lindberg, has given a very nice quote, which I'd like to just put in full here. So cosmos has been commonly used to buttress the claim that medieval people believed that they lived on a flat earth. This claim is totally false. Cosmos is, in fact, the only medieval European known to have defended a flat earth cosmology, whereas it's safe to assume that all educated Europeans, as well as sailors and travellers, believed in the earth's sphericity. Now, I don't want to just take Lindbergh's words, but I'll give you a couple of examples of people in the Middle Ages talking about the spherical earth. We begin with the Venerable Bede in 703, his work on the nature of things. This is a quote. We say the sphere of the earth, not because it has the shape of a perfect sphere, in view of so great a disparity of mountains and plains, but because if all of its perpendicular lines were enclosed within a circumference, it would make the figure of a perfect sphere. And therefore it appears that the stars of the northern region always appear to us, but never those of the southern region. And in turn, these northern stars are not seen by those people because they're blocked by the globe of the earth. The country of Egypt does not see the constellations, the Great and the Little Bear, and nor does Italy see Canopus. Now, this is a way of explaining that why do we see different constellations in different parts of the world? It must be because of the sphere. That's B. The second person we come to is William of Conch from the School of Chartres. Now, William, on his work on philosophy, 1124-1130, wrote, "If the earth were flat, the city position in the east would experience morning and midday at once, from where indeed the sun would appear for them. It would be above them. In truth, the city position in the west would have midday and evening at once, since therefore for everyone there is an equal space from morning to midday, and from midday to evening, it is clear that the earth is not flat but round, for which reason in the east, dawn and midday are sooner than in the west." And William didn't just want you to actually take his words, he actually put a diagram. And this is one thing you find in medieval science, as I point out throughout today's paper, that medieval people or people working with science, scientific ideas, were constantly trying to show their ideas in different formats. We'll go for the third of our people talking on the spherical Earth, and this is Johannes de Sacrobosco, his work called On the Sphere, and he describes the oceans. So, thus, that the sea has a bulge and is approximately round is shown thus. Let a signal be set up on the seacoast, and a ship leave port and sail away so far that the eye of a person standing at the foot of the mast can no longer discern the signal. Yet if the ship is stopped, the eye of the same person, if he has climbed to the top of the mast, will see the signal clearly. Yet the eye of a person at the bottom of the mast ought to see the signal better than he is at the top, as is shown by drawing straight lines in both to the signal. And there is no other explanation of this thing, or this phenomena, than the bulge of the sea. Therefore, the sea is round. Now, the picture I have accompanied with this is not actually from Johannes de Sacrobosco. It's from a 15th century Icelandic manuscript, and showing here the legend of St. George and the Dragon, which you can see at the bottom. But what I wanted to show you this was because it shows the very same thing that Sacrobosco is talking about. The ships are coming up, they're going over the horizon, and they're going down on the other side. The writer, even though the artist, even though he's depicting a scene of a saint's life, still showing that the earth is a sphere. Now, we move from the flat earth to the early development of science in the Middle Ages. Now, of all of the periods of the Middle Ages, the so-called Dark Ages, from the fall of the Roman Empire to roughly around 1000, is the most belittled and benighted of all of them. The Dark Ages, nothing happened, everything was stasis, it was the worst times. But this is not true either. So this is from the end of that Dark Ages period, from around the year 1011. This is Bridgeworth of Ramsey. He was a monk who wrote his work as Enchiridion on the subject of computers, the calculation of Easter, and he also included astronomy and many other things as well. And he also included many wonderful charts and diagrams. Now, the Christian science of computers, and here we have the Council of Nicaea in 325, where he decided about this, revolves around certain things. First of all, the date of Easter. Easter commemorates the Passion, resurrection of Christ. Easter took place during the Jewish feast of Passover. Easter begins at the 14th day of the Jewish lunar month of Nisan, the first month of spring. This is a full moon. Easter is celebrated only on a Sunday. So to calculate Easter, one has to know the solar and lunar calendar and somehow harmonise them together. This is incredibly complicated because they don't fit in perfectly at all. And there's a massive host of variants which it would take a long time to go into, but basically they don't fit and they have to be worked in many elaborate ways to make it work. However, what it did do was this complicated process led to an explosion of astronomy and maths to calculate the date of Easter. And one of the most prominent calculators, we've met him before, now we're meeting again, is the Venerable Bede. So, Bede was a Benedictine monk at a Northumbrian monastery of Wearmouth Jarrow. Now, again with the thing of the Dark Ages, a time of not much literature, Bede had access to a library of around 500 volumes. Okay, not so great compared to like the library we have here, but for a personal library it's a lot. He used 175 different sources in his works, which is also a massive amount. He was a very educated and learned man. In fact, he calculated Easter up to the year 1063 using a 532-year cycle where every single Easter would be put into the right date. But not only that, he didn't just use mathematics. He also worked out, and using his own experiments, made a complicated sundial which he could use to keep track of equinoxes. By using this, he found out that the leap year system, which was used, we still use today, 365¼ days, was not entirely accurate. And so he made calculations to change that accuracy. Not only this, he actually went out to measure local tides, and if you've ever been to Northumbria, there is a big tidal system, very, very low-lying beaches. It's possible to work out the tides, and he used also this information when he, with his calculation of the phase and orbits of a moon, to work out the effect of the moon on tides. Now, there was a Renaissance, or we know as the Renaissance of the 15th, 16th century, was not the only Renaissance. There have been several in the period of the Middle Ages, and the first one of these was the Carolingian Renaissance. Now, this is Charlemagne, the emperor, crowned emperor, first emperor of the West since the fall of Rome in year 800 by Pope Leo III. He instituted a program which established in every monastery and diocese in his vast empire, and it stretched all the way from the Pyrenees, almost to the border of Denmark, over into Eastern Europe and to Italy. A school which taught Latin literacy, the Bible, music, and also this theory of computers. So to do it, they needed a textbook or a handbook which contained explanations of complicated astronomical concepts. This was created in the Aachen Conference of 809. Now the Aachen Conference is very interesting because in many ways it's like a conference that we have today. All of the greatest scholars of the age were brought over to Aachen, and they put all of their different knowledge in, whether it be of computers, of astronomy, weights and measures, mathematics, and together they worked out a huge 7-volume edition which was then copied and sent around the empire. This beautiful diagram here is a page from one of these copies. It also used classical authors, which, contrary to a lot of popular belief, were not forgotten in the early Middle Ages. These are Pliny, Plato, Probius, Martianus Capella, and this shows an example from Martianus Capella, which will be very interesting as we go later into the discussion. This is a picture of the Earth. These beings going around it are representations of the planets. Here are the zodiac, is the zodiac. Now, we can see, for example, here's Mars in his Phrygian hat. We have Jupiter represented as an eagle, and here is the Sun. Now, what is important here is that, of course, in the Middle Ages, people believed that the planets go around the Earth, and so does the Sun. But Martianus Capella was pointing out that actually Mercury and Venus go around the Sun, and they, as a whole, go around the Earth. Now this is very important because this is the beginning of a heliocentric theory. This continues throughout the Middle Ages. Martianus Capella is one of the most read and commented authors of all, and it has great implications, as we'll see later on. So now I'm going to move to one of the great figures of the Carolingian Renaissance, just to show you an example of some of what we were doing in this time. This is Alcuin of York. He was also from Northumbria, not taught by Bede, but his master himself was taught by Bede. He was the advisor to Charlemagne, and he wrote the first Latin treatise on mathematical problems, the propositions for sharpening youthful minds. He used 53 mathematical questions, and I'm going to show you number 42, just to give you an example of what they do. So question. There's a ladder which has 100 steps. 1 dove sat on the first steps, 2 doves on the second, 3 on the third, 4 on the fourth, 5 on the fifth, and so on up to the 100th steps, which has 100 doves. Let him say, he who can, how many doves would there be in all? I don't know if any of you are very good mathematicians and can kind of get that quite straight away, but just to show you this working out, take the dove sitting on the first step and add it to the 99 doves sitting on the 99th step, thus getting 100. Do the same with second and 98th steps, and you'll likewise get 100. By combining all the steps in this order, that is one of the highest steps with one of the lower, you will always get 100. The 50th step, however, is alone without a match. Likewise, the 100th stair is alone. Add them all, and you will have 5,050 doves. Now, Carolingian scholarship was driven by Charlemagne, and this is something which I will also go back to, or will continue. That science was quite often driven by patrons, and the patrons weren't always ecclesiastical. They were quite often rulers, in this case Charlemagne. Now we know from his biographer that Charlemagne learned the art of computus himself, and with great keenness and curiosity investigated the course of the stars. Not only that, but one of Charlemagne's daughters also studied the stars of the heavens at night, and was accustomed to ceaselessly praise the powerful God who adorns the firmament with constellations. The monk Dongle of Saint-Denis corresponded with Charlemagne, because Charlemagne was very interested in the 2 solar eclipses that happened in the year 810, and he was also very interested in the orbit of Mars. We also have one of the other learned scholars of this period, Probanus Maurus, said to be the most learned man of his age. He went further into time and actually worked out that the week can be divided into a tiny measurement of time, which he called atoms. 3,790,800 of them make 1 week. And finally, the nocturne, a major aid to astronomy, was discovered by the Carolingian scholar Pacifius of Verona. And here we have, from one of Pacifius' manuscripts, the nocturne. Now, a nocturne basically is a telescope without lenses. And so you have 12 dividing points here. But with the nocturne, balanced as it is on a plinth here, can give a very accurate pinpointing of stars. Similar to Tycho Brahe in his later time, he never actually used telescopes. He used a lot of the old traditional ways of doing things. The nocturne, one of the first ones of this. This comes along this Carolingian period. Now, move from the Carolingian to one of the most important parts of science and how science was developed in the universities, but to point out some of the characters or the innovators along the way. And first of this, Pope Sylvester II. The Pope, often called the Scientist Pope. His birth name was Gilbert Aurillac. Benedictine monk, traveled to Barcelona and studied works of astronomy, mathematics and geometry compiled by Islamic scholars in the Caliphate of Cordoba. So Gilbert described the use of an instrument called the astrolabe in astronomical and geometrical problems. He also used the armillary sphere, which is this instrument here, to fix the position of the pole star and record measurements for the tropics and the equator. He also developed the first hydraulic organ in Europe, using steam to produce sounds. And hydraulic organs that we have can tend to be based from this one. And it was all to notation because he wrote many books on music as well and musical theory. He also developed an abacus and introduced Indo-Arabic numerals to Europe. And this is one of the great stages. The Indo-Arabic numerals changes everything, all mathematical calculations. Finally, he was made Pope in the year 999, but only lasted for 3 years before he died, unfortunately. And just to show you, this is the astrolabe. This is a very important instrument used throughout the Middle Ages, developed from the Caliphate of Cordoba was one of the great places to make this, but you find it in other parts of the Islamic world as well. Taken and then used in the European standard. I have here a picture of a manuscript here where shows 3 monks working together. Chief monk here, using the astrolabe, looking up the stars, making his calculations. This monk here has a manuscript open which is showing astronomical tables, so he's using the tables to calculate with the astrolabe what he's looking at, and the third monk is writing down and continuing these calculations. So what we're doing is, it's not knowledge which is just passed on, here is a load of stars, this is where they stand. They're continually changing, adapting and making new knowledge and new information. Here we have another user of the astrolabe here. This is Herman Verlaine, or Hermanus Contractus in his Latin form, of the monastery of Reichenau. Now he was extremely disabled, he had very limited movement, limited ability to speak, he had to be carried around on a special chair, but he was a great genius. He was one of the key figures to transmit Islamic mathematics, astronomy and scientific instruments from Islamic sources into Central Europe. And his works contain a description of the astrolabe, which of course he has in his hand, as well as star charts with data correct for the latitude of Reichenau of 48 degrees north, and he also was able to use this information to make a new calculation of the diameter of the Earth. Now, it was not only men who were involved in medieval science. We've already come across Charlemagne's daughter, who obviously showed a great interest in astronomy. And we go to Hildegard of Bingen, German abbess of the Benedictine order, very well known for her visions and her music, which is still well admired today. There's a picture of her achieving her visions here. But she also compiled 2 scientific works, Physics and Causes and Cures. Physics is quite a very interesting work. It's actually 9 books and contains information on over 1,000 different plants and animals. As well as having details of herbal medicines as cures, what's very interesting is that lots of these observations are detailed observations of local natural phenomena around the abbey. So these are things that either her or her nuns have gone out and observed in nature, and then she has written them down. Now we'll move to another of the female scientists, and this is Trotta of Salerno. Salerno in southern Italy had many single master schools which centred on medicine, and these schools produced and developed medical texts which were then copied and used all over Europe. Henrik Harpestrand in the 13th century translates some of the works and adapts them into Danish, which then comes all over Scandinavia. Most important figures of the Salerno schools was Trotta of Salerno, who lived in the mid-12th century, and she wrote on treatments for women and practical medicine, according to Trotta. And this was one of the most popular works of medicine in the Middle Ages. Now we had the royal patron of Charlemagne, and I will now move to a different royal patron. This is Roger II of Sicily. So Roger II developed a court of classical Greek and Arabic learning at Palermo, personal interest in mathematical geography, mathematical geography, and devised instruments for measuring longitude and latitude. So he worked together with the Islamic scholar Al-Idrisi to create the Book of Roger, which is a great work of cartography and astronomy. What's interesting with this work was that Roger interviewed scholars and first-hand observers singly and then also in groups until consensus was achieved. So it wasn't just one person's idea, it was a lot of people, the best people of the age, working together, and they were Greek, they were Norman, and they were Arabs and Jews, working together to create this great work. And this is part of the Book of Roger here. So one of the fantastic maps, we can see that it contains many of the things we have. We see Denmark is up here, and the British Isles, of course Italy and Sicily are very well detailed. and the map stretches all the way down to Indonesia. So move from Sicily to the medieval university, one of the most important of all medieval discoveries. In fact, we wouldn't be sitting here if it wasn't for it. So, little introduction. 11th century, cities had started to form their own corporate initiatives, corporations and guilds. Members of various trades formed guilds or universitates. They were autonomous and governed by their own laws. So masters and students in the cathedral schools that have been set up by rulers such as Charlemagne followed the guild movement, and so therefore started to form their own universitates, universities. To give you an idea of how university learning was structured, how you would understand or how you would learn something, for example, like astronomy. So lectures were based on prescribed texts. I'm going to show you a few of the texts in the next slide. The master read the text that he lectured on and explained it. Any noteworthy points were then considered, and finally the questions that arose from those texts. Then in disputations, set questions were debated, objections and replies were presented by successive opponents, and respondents ending with a final resolution or determination. So there was a lot of debate going on in the university. Study books, and we have now students quite often, unless they're from very, very rich families, wouldn't be able to buy an entire book. So the books were divided up into sections, Pekier, which became the Pekier system. Students would rent them section by section, copy them, make notes on them, and return the original back, which would then be rented to the next student. Johannes de Sacrobosco, who we've met before, English master of Paris, wrote several popular study books on what are called scientific subjects. Art of Numbers, taught arithmetic procedure using Arabic numerals. On the Sphere, which we've seen a little bit before, and we have an image here. This is from a manuscript belonging to a Danish scholar who brought it from the University of Paris and brought it back to Denmark in the turn of the 14th century. It shows solar eclipse. And The Reckoning of the Years, which was on Computus. Now, it wasn't just small books, but also a wide variety of encyclopedias, which range from small compilations to the enormous great miracle of Dominican Vincent of Bouvet. In a modern edition, this consists of 4,500 double-columned pages. There's a lot of information in that one book. So I'm going to move now to a learned chancellor, and this is of Oxford University. This is Robert Grosseteste, Latin big head, known for his great amount of knowledge that he had, Bishop of Lincoln and first Chancellor of the University of Oxford. Grosseteste concluded that mathematics was the highest of all sciences and the basis for all others, since every natural science ultimately depended upon mathematics. He also worked with his own theory of scientific demonstration, which he called resolution and composition. Both should be verified through experimentation to confirm the various principles involved. And his most interesting work, and one which a lot of work has been done on lately, both by medieval scholars and also cosmologists. So his work on light explores the nature of matter and the cosmos. So 4 centuries before Newton and 7 centuries before the Big Bang Theory, Grosseteste described the bursts of the universe, an explosion and the crystallization of matter to form stars and planets. Now, one of Grosseteste's most well-known students, Roger Bacon, an English Franciscan master at Oxford but also at Paris, wrote the greater work, which is treatment of mathematics, optics, alchemy and astronomy. He also put lots of theories on positions and sizes of celestial bodies. But Bacon actually went further than Grosseteste, in giving mathematics primacy as the origin of all knowledge, as well as theological understanding. Now, Bacon's also interesting because he had many visions for technology of the future. What might happen in the future, even though he could see that in his own age things wouldn't be able to be achieved, but something might be done in the future. And these are some of his observations. See what you think. Machines for navigation can be made without rowers. So the largest ships on rivers or seas were moved by a single man in charge with greater speed than if it were full of men rowing. Also, carts can be made so without animals they will move with unbelievable speed. Flying machines can be constructed so that a man sits in the midst of a machine revolving some engine by which artificial wings are made to flap like a bird. A machine can easily be made for walking in the seas and rivers, even to the bottom, without danger. Never made any of these, but he had the vision to see that they could one day could happen. So I'm going to move to a Danish example, which is Petrus de Dacia, a canon of Roskilde. We know already in 1274 that an unnamed astronomer, and which is probably him, belonging to a chapter, made a series of observations of the altitude of the sun at noon, from which they calculated the length of a day by sine quadrant, astrolabe, and astronomical tables. He was a master of the universities of Bologna and Paris, where he taught mathematics and astronomy. He also wrote 14 extant treatises on mathematics, geometry and astronomy, of over 200 medieval manuscripts survive today. Now what Petrus is very good for is that before him one had to use a set of 6 separate instruments for calculating longitudes. Petrus is the first to invent a device for solving this problem for all of the planets with a single instrument. And his second achievement was in the field of astronomical tables, which his calendar remained in constant use for the next 150 years. So I'm quickly going to move again to court of learned monarchs, just to show you that some of the other ones here. Frederick II, Holy Roman Emperor, known as Super Monday, the wonder of the world, for his learning, founded the University of Naples. He attracted scholars to his court such as Michael Scott, where he translated scientific works from Arabic into Latin. Fibonacci, the famous mathematician, was the imperial mathematician. The Greek John of Palermo and the Arab Theodore of Antioch were described as the emperor's philosophers. So yet again, he was using Greeks, he was using Arabs, and translating works in his court. In fact, he sent questions of mathematics and philosophy to Muslim scholars throughout the Mediterranean and kept his correspondence going in his life. He even wrote his own book, which is where this image comes from, The Art of Hunting with Birds, a scientific book approaching the subject from Aristotle, but based closely on observation and experimentation throughout. The other enlightened monarch we would like to bring up here is Alfonso X, Alfonso the Wise, King of Castile and Leon. He also employed Jewish, Christian and Muslim scholars at his court, and primarily for the purpose of translating books from Arabic and Hebrew into Latin and Castilian. 4 of the major scientific works we have here are the Alphonsine Tables, a book of wisdoms of astronomy, a book of judgments of astrology, and a lapidary, which is about precious stones. And the Alphonsine Tables then became the most popular set of astronomical tables in Europe. Let's move further with medieval astronomy and physics. To show, I'd like to show here, the Merton calculators from Merton College at the University of Oxford. This is a picture of Merton College, pretty much still standing as it was then. Now this is a school of people who work together, working on problems to do with physics. They formulate mathematical rules, different types of motion, changes in speed of moving bodies. They measure the alteration of degrees of intensity of physical qualities, such as cold and heat. Thomas Bradwardine was the head of calculators, who wrote his treatise on proportions. And so he's developing Aristotle's idea of velocity. A moving object is proportional to the moving force, inversely proportional to resistance of the media. And he also anticipated the concept of exponential growth. Also from Merton College was William of Ockham. Now William of Ockham wasn't actually a scientist as such, but his work, or his Ockham's razor, is a very useful tool for doing this. The term razor in itself versus distinguishing between two hypotheses, either by shaving away unnecessary assumptions or cutting apart two similar conclusions. In his own words, it is futile to do with more things that which can be done with fewer. Another of the great physicists, Stanford University of Paris, Jean Buridan, was followed the Byzantine scholar John Philoponus and the Persian polymath Avicenna, and proposing that motion was maintained by some property of the body, imparted when it was set in motion. And so he named motion property impetus from a term impressed force used by Avicenna. So, after leaving the arm of the thrower, the projectile will be moved by an impetus given to it by the thrower and will continue to move as long as the impetus remains stronger than the resistance, and would be of infinite duration were it not diminished and corrupted by a contrary force resisting it or by something inclining it to the contrary motion. So what he did was he moved the two-stage theory of Avicenna to a third stage. So the initial stage, motion is in a straight line, you see from this manuscript here, with the canons describing the movement. Motion in a straight line in the direction of impetus is dominant, while gravity is insignificant. The path begins to deviate downwards to a straight line as part of a great circle as air resistance slows the projectile and gravity recovers. And gravity alone draws the projectile downwards vertically as all the impetus is spent. Been used for term gravity, but this is what they're referring to. One of the great astronomers, one of the students of Buridan was Nicolas Orem, also at the University of Paris. And he was interesting because he discussed the range of evidence for and against the daily rotation of the Earth on its axis. And he actually maintained that if the Earth were moving and not the celestial spheres, all the movements that we see in heavens that are computed by the astronomers would appear exactly the same as the spheres were rotating around the Earth. Now, Orem actually believed still that everything revolved around the Earth, but he could see that it could be possible to look at it another way. We have great astronomers here. Regiomontanus, a German astronomer studying in Leipzig and Vienna. Now, he's very interesting because he established the first scientific printing press in Nuremberg and published the first printed astronomical textbook, New Theories of the Planets. He actually established Nuremberg as a centre for astronomical and mathematical studies and observed the comet of 1472. He estimated its distance to be 13,120 kilometres and the diameter as 129.6 kilometres. Of course, they're not correct, but they show that he is aiming to be correct and that he is able to be dealing with thousands of kilometres to try and get his ideas forward. It is believed that possibly Regiomontanus actually was coming close to a theory of heliocentrism before he passed away. Now, one other development of this time is the astronomical clocks. So it wasn't just the use of astronomy and the astronomical instruments, but clocks themselves. Hourglass has already been used as timekeeping devices since the Carolingian Renaissance. They were already common by the 14th century, and by this time the earliest clocks were invented. We don't know who invented the very, very earliest clock, but certainly the first astronomical clock was the Abbot Richard of Wallingford in St Albans in the 1330s. The wonderful clock we're looking at here, it was created by Nicholas Lilienfeld and is in Lund Cathedral, where it has sat there since 1420, which of course then was medieval Denmark. And Petrus Astronomus, a German monk from Vadstena monastery, created an astronomical clock in Uppsala in 1506. Now this was useful because even if you had no access to an astrolabe or another device, you could actually go to the astronomical clock and use it. And the four figures that surround it are all important astronomers. We have Ptolemy, Alfonso X, Harley Abbas, and Albumassar. So one of them is the Greek astronomer Ptolemy. Alfonso X we've come across, and 2 are Islamic scientists. This stood in Lund Cathedral, right next to the shrine of the Virgin Mary in the holiest of holy places, and people would look up and see these 2 Islamic scholars, and didn't obviously see something wrong with it. And just to give you an example of some astronomical manuscripts that I've been looking at, we have an Equatorium. This is a fragment from Norway, the 15th century, and Peter Albertson, who was the first Vice-Chancellor of Copenhagen University, brought with him his own astronomical manuscript and from the University of Cologne, and donated it to the library. What is called is a Volvel here. What I'm showing you these briefly is these were being able to be used on paper, what can be done with the clock and what can be done with the astronomical instruments. Okay, so I'm realizing I'm actually running a little bit out of time, so I'm going to have to skip a few things here. But I will just quickly move to medicine. So Theodoric of Luc, Italian Dominican surgeon, he stressed the importance of personal experience and observation instead of relying blindly on ancient sources. The practice of Galen, of encouraging the development of pus in wounds, was wrong, so I believe, and he had a more antiseptic approach, with a wound being clean and closed to promote healing. Bandages were to be pre-soaked in wine as a form of disinfectant, and he also used anesthetics, sponged, soaked in dissolved solution of opium and other substances held beneath the patient's nose to induce consciousness. And Mondino de Luzzi, Italian physician, anatomist, professor of medicine at Bologna. He was the first to incorporate a systematic study of anatomy and dissection into medical curriculum. And he formed the first public dissection in Bologna in 1315, which was formally sanctioned by the Vatican and was in fact the first officially sanctioned genome anatomy since the 2nd century before Christ. And his work was one of the first true anatomical texts. Also using this kind of personal experience, I want to just quickly bring you to 2 battlefield surgeons. John Ardern, English surgeon, member of Guild of Surgeons. He also recommended opium for pain relief and as anaesthetic. And he saw active service in the 100 Years' War, and the injuries he saw informed his medical writings for 3 decades. And this is a beautiful scroll, now kept in Stockholm, brought over by Philippa of Lancaster. Ardern was surgeon to her father, and shows many of his different treatments. John Bradmore, English surgeon working as court physician through reign of Henry IV. Sorry, it should be Henry V. The Battle of Shrewsbury in 1403, King was shot below the eye of an arrow, and Bradmore invented an instrument that could be used in extraction. He guided it into the room to extract the arrowhead successfully. The wound was then filled with wine to cleanse it. So yet again, these are people who are using their observations to create newer and better medicine. And we'll just finish for sexual medicine with some more Italian female physicians. Bella of Salerno is a mid-14th century Roman physician, taught medicine at Salerno, lecturing on medical practice and women's health. Rebecca de Guana, Italian physician and surgeon also at Salerno, worked on fevers, on urine and on the embryo. Mercuriade worked on crisis, pestilent fever and the cure of wounds. Constance Calenda, Italian surgeon specialising in disease of the eye. Her father was a dean of the faculty of medicine at the University of Naples. Dorothea Bucca was an Italian physician. She held a chair of medicine and philosophy at the University of Bologna from 1390 all the way to 1430. And finally, Clarice del Torricio, Italian physician and surgeon who specialised in diseases of the eye. So I just wanted to point out that quite often it seemed that there wasn't female surgeons, wasn't female people working what we call science today, but certainly in the case of Italy, that's not true. Fortunately, because of time, I'm going to have to quickly skip through some sections here. Can I just quickly... Yeah, so I had to jump, sorry to miss out about medieval technology. But just to go back to our idea of the flat Earth, and where did it come from? We're going to Washington Irving. He wrote a history on the life and voyages of Christopher Columbus, best-selling book. We've seen at Dominican convent of St. Stephen, Salamanca. Washington Irvington says that learning was walled up in monasteries, all professors were monks. Columbus was a visionary and natural genius. The lights of antiquity had been stamped out and learning had receded. Mathematics was not allowed to contradict scripture. The idea of a flat earth was seen as a fable, whereas for great Columbus it was a simple and obvious idea. The professors all thought the earth was flat and the sky like a tent, just like it says in the Psalms. Just to show Columbus here, he did read Ptolemy, Pliny, travels in Marco Polo. However, he misread Alfagani, mistook an Arabic mile for a Roman mile, so therefore he thought the world was 30,200 kilometres in diameter, not 40,248 as Alfagani put, and actually Alfagani was very close to the figure. Ptolemy believed Eurasia as 180 degrees of longitude wide, so actually 150. Columbus instead followed Marianus of Tyre, and his figure was 225. So when he actually came and faced the Dominicans of Salamanca, they were saying he was wrong, not because they believed in a flat earth, but because his mathematics were rubbish. So we move now to The Swerve, the best-selling Pulitzer Prize by Stephen Greenblatt, who takes the story of Poggio Bracciolini at the Renaissance, discovered the only copy of nature things by Lucretius, therefore heralding the Renaissance, and yet again he falls straight into the trap, continuing with Irving, ignoring all scientific learning between Lucretius and the Renaissance. And this is a long line which started with scholars in the Renaissance, continued to Protestant Enlightenment scholars, carried on with Irving, and still, unfortunately, continues in today with Greenblatt. And just the last two slides, I just want to quickly show you that two of the greatest scholars of the early modern period, who we consider to be the big change, the jump from medieval science to modern science, Copernicus. He used Martianus Capella's work on the heliocentric orbits of Venus and Mercury to develop his own heliocentric theory, and thanks Martianus Capella in his own work for coming up with the theory. He used many works of Greek and Islamic astronomers, especially the Arab Al-Battani. He used the works of Jean Buridan, Nicolas Orem, to put forward the idea of the rotation of the Earth. And finally, Copernicus used the mathematical and trigonometric techniques he gained from the works of Montanus. He made believe that he was standing on the shoulders of giants. And finally, Galileo. Claimed much originality for his discoveries, but his famous falling bodies experiment, we see him doing here from the town of Pisa, had already been mentioned by John Philoponus, Byzantine scholar, in the 6th century. Thomas Bradfordine had said with this experiment that it would have worked with the same result it had been in a vacuum. Giovanni Benedetti, Italian mathematician, had actually produced his own results 50 years before Galileo in Italian, German and in English. And Simon Stephen, a Dutch engineer, published the account of the same experiment in 1556. Galileo's impetus theory had also been written about by Philoponus. Avicenna, the Merton calculators, Jean Buridan, Nicolas Orem, and Albert of Saxony all wrote about this theory. And finally, the Spanish Dominican de Soto published a theory in 1551. So I hope that in my paper I've been able to give you some idea of the scope of medieval science, that modern science, that it wasn't a big dark period, and that we are in many ways standing on the shoulders of those who have gone before us. Thank you.
Thank you very much, Christian. We have maybe time for questions. There are already questions, I think.
Can I ask? I mean, was Galileo actually aware of these previous studies?
Yes, Well,
Okay.
certainly he was aware of the ones that have been published. But yes,
Okay.
So,
So what was the merit? I mean, of Galileo was putting together all these different
Galileo was the
contributions,
great,
or
he was the great publisher. And certainly
Okay.
he was, his great discoveries with the telescope, definitely not to be taken away
Mhm.
from him. But he was a great publisher, so he was able to put forward a lot of these theories and claim them as his own.
okay.
One of the things we, to stay with Galileo, credit him with in physics education or physics teaching is to say that, I didn't know about all these people moving forward, but one of the things we credit him with is the numerics. That he claims that not only do heavy and light objects fall at the same rate, but also that how acceleration works, meaning that the distant covers goes as the square of the time. Was that published by any of the others, do you know? Or was it indeed published by Galileo? I mean, we attribute it to
That,
Galileo, but I don't
that I
know if you
couldn't
knew
say.
it. Sorry?
That I couldn't say. I'm
Because-
not sure.
A lot of the things you say about the earlier physicists, sort of
Mhm.
what I would though call pre-physicists, is to say that they have some of the generalities right.
Mhm.
And this is something I didn't know, and it's of course very important. But the thing that really changes with Galileo, with Kepler, and with Newton is that we get numerics. We become able to make exact predictions about these things.
Well, certainly, I mean, with the physicists, I believe at least the Merton calculators were already starting to make these calculations with physics. Some of their work is published. Of course, they're not taking away yet again from Galileo and setting off from Kepler and the others. But certainly the beginnings of what they have done is coming from the medieval period.
Do we know anything about what the common man thought about the shape of the Earth?
Much harder to work out because we have very little evidence of what people thought about such things. We know, for example, that Holberg has his famous play Erasmus Montanus, where he gets the university-educated scholar, comes back to his village and starts to talk about the spherical Earth, and everyone mocks him because they believe in a flat Earth. Now, I'm not sure if Holberg is using actually experiences from his own, experiences, or whether this is a kind of common theory. But certainly, what Sacrobosco has described, and what I can show you, what I showed you with the image of St. George the Dragon, that people who are on boats can see that the Earth is spherical. It's a kind of a common sense way of seeing things.
Just to briefly follow up on that, non-scientific writers also describe the Earth as round in this period. So I mean, that doesn't get you the common man per se, but it does show that it's a wider phenomenon.
And also to follow up on that again, in church art and architecture, Christ is often depicted as sitting on the earth, which is round. So the common man would see spherical depictions of the earth. So there is no reason to believe that the common man thought the earth was flat. Every single piece of evidence we have points to the opposite direction. So most likely, all people who came to a church which had a depiction like that, either on the exterior decorations or inside the church space, would know that the earth was in fact round.
And also to follow up as well, often depictions of an emperor who would be holding the orb as a symbol of office, and the orb represents the earth.
Other questions?
Have you been able to do any work on the transmission of knowledge that is not only physical, I mean, how was the knowledge transmitted from one person to another, and were there specific routes that things followed, and was it in the form of with manuscripts being sent back and forth and so on?
Yes, well definitely it was the manuscripts, and they quite often had their evolution. First of all in the earlier period, in the cathedral schools, then into the universities, and say for example in Scandinavia, they would originally come from the great universities, especially Paris being one of the great centres for Scandinavian scholars. But then later, in the end of the medieval period, the universities of Copenhagen and of start to develop their own ways of producing these manuscripts. What also is interesting is that scientific knowledge isn't always used in kind of one of the great classical languages of the age, Greek, Arabic or Latin. But as time goes on, the languages start to appear more and more in the vernacular. And especially medicine is one of the earliest works which are translated into vernacular language and then transmitted around other places.
At the end of the first part of your presentation, you mentioned that in Italy there were, at around the 15th century, there were many female physicians. So, I mean, are there any particular, and then you, if I got it right, you mentioned that this was a very particular case. So, is this, I mean, are there any particular reasons for this? I mean, some cultural reasons?
Well, it's definitely something I'd like to go into, and I think any Italian medievalists in this room would be better able to explain this phenomenon than me. But certainly, from the very beginning of the school of Salerno, we already have female scholars. It's interesting that you have Hildegard of Bingen in Germany, but then later the kind of female scholars, doctors seem to kind of dry up in Northern Europe, but certainly in Italy still popular. In Byzantium, is there any cases of this?
Francis,
Yeah.
no, sciences.
No.
Not off the top of my head.
No, but certainly it's a very interesting case, and especially as I showed you, that you actually had chair sort of medicine and philosophy
Exactly,
being
yeah.
women.
Yeah.
So it's definitely something which is very overlooked, and I think there needs to be a lot more work done into this, and a lot more work done into their own. I think a lot of their works are not actually published, so there is a lot of work for scholarship over the next coming years on this particular subject.
So thanks a lot for your talk, and so you covered kind of almost a 1,000-year period here, and of course you talked about a couple of people and works. Can you give us a little more of a feeling whether that was a continuous process or a little steady trickle of discoveries that were picked up and so on, or was that I don't know, more discontinuous? So there was a couple of people whose discoveries sometimes I think they were works that were lost for a long time as far as I remember, and then picked up. Was that just 2 or 3 stages, or was that more continuous trickle?
Well, you certainly have the most important stages are the translation of Arabic works into Latin, and this starts off already in the time of Jabir Kovorilac in the end of the 10th century, becomes very, very important in the 12th century. The fall of Constantinople, 1204, then you suddenly have, in the 13th century, you have a lot of manuscripts which then come over from Greece. These are 2 big things. Then the universities for the kind of correlation of these ideas, and then the spread of ideas. These would kind of be what I would consider like the big changes. Then you have the universities then become the most important places, and certain universities then focus on certain things. So for example, Italian universities of medicine, Oxford on physics and astronomy, and so these start to then produce lots and lots of material. One thing certainly that the more I've looked into it, the more that science, medieval science, has been vastly overlooked. There are thousands of manuscripts which have never been looked at, only cursorily, looked in, seeing what maybe they're talking about, and then that's it, catalogued and never looked at. There's whole treatises which have never been, never had editions, let alone translated. So I believe that the movement of medieval science was on a far bigger scale than we have been led to believe, because we have been led by, unfortunately, like Galileo and also Washington Irving into believing that the past or the medieval period didn't have these movement of ideas. I don't know if that's answered your question.
Yeah, that's great. Thanks.
suppose the idea of if I take the word, the idea of rediscovery is in a sense a question of where things are and have they been there before. So you could say in the sense that Greek learning was everywhere around the Mediterranean in ancient time, but not at a certain period later, and then it sort of came back partly through Arabic translations and such. So in that sense, it's a sort of rediscovery or reappropriation, but it's not that it's been gone, it's just been perhaps somewhere else.
Well, absolutely. But what is very interesting, and with refining these works, is it's not just finding a new copy of Ptolemy's Almagest in astronomy. It's actually what people are doing with that work of Ptolemy. So when these works come in from the Islamic world, they're not coming just pure. They're coming with lots and lots of commentary, because Ptolemy's not correct on anything, he's not correct on anything. But people are correcting him. And the way that people are, for example, in astronomy, they're using instruments to make their own observations to make better the corrections. That the doctors are not just taking rediscoveries of Galen, but they are actually using their own experiences to make better versions. For me, is the kind of like, science is the sort of like the new discovery and the really important thing. And even back in the Carolingian period, Martinus Capella, for example, is not just copied verbatim, he is commented on, and every little piece that he's talking about as astronomy is picked apart, and then it's put into new commentaries, and then these commentaries are picked apart, and new things are added to them. So it's a constant putting of ideas together to create works which in many ways are quite different from what they were originally, when Martinus Capella or Ptolemy first wrote them.
What is the reason? I mean, you may not know this, but do you know the reason why they take up, well, I just forgot the English word, autopsy of human bodies again? Is that because they've read about it and they sort of discuss that this is an interesting approach, or because it seems quite a radical, even with such a long gap?
No, I don't know. I mean, the only thing, as far as I know, was because it was needed. Because they wanted to understand further, but they couldn't dissect bodies. But, and even Galen was only able to dissect on animals, or sometimes in the gladiator schools where he was working as a doctor, and sometimes we look at some of the bodies, we're not actually kind of cut them into pieces and look at them. So yeah, it is a big jump, but I think it shows very much the kind of investigative spirit of the age that, first of all, it's thought of, then allowed, and also sanctioned by the Vatican to actually take place.
You mentioned battlefield physicians as well, and presumably throughout the entire period there was a kind of practical medical knowledge that was developed and passed on about the treatment of wounds, and also when you see certain parts of the body exposed at different moments and so on. So when I think we see the textbooks are the great books of this, but there must have been a more familiar kind of knowledge that was developed and passed along.
Absolutely, and I think it's very interesting when you read the text from the people who these like battlefield surgeons, that they are actually having to come, to make up a new idea on the spot. Henry V would have died had there not experiment happened and is able to be treated. And so therefore that was one of those moments where you just had to make an on-the-spot decision, and a new discovery was made. And then of course that worked, he survived for many years afterwards, and then that could continue. So I think it is, really using ideas, and not just trusting on what Galen has said 1,000 years beforehand.
That may be it. So should we thank Christian once again?